Astronomical units. My name is Ryan Heron. It's my new name. And welcome, all of you. Thank you for coming to our biggie. Once a year in December, we pull out all the stops and give you the best. Even though we're not looking at people from JPL and Caltech, we got astronomy professors from City College and former teachers who retired.
Recording in progress.
Oh, come on, lady, give me a break. Someone that called and trying to sell me something. We have to have your ugly picture up there, Tom?
We'll be back.
Why isn't your picture? I'm the one sitting here in front of the lens. Doesn't make sense. It's the night of the elections. It's also the night of our, what I call in-house, members-only speakers. You've been seeing their pictures. And I just want to tell you real quickly that I was at the LCO downtown second Thursday of the month. I think it's second Thursday, their big astronomy on tap at M Special bar. Ran into a guy from LA and his wife who was dropped in on us a couple times. He couldn't make it tonight, but he was raving about this club, and he was a member of the LA Astronomical Society that meets at Griffith Park. And he said, I checked out your website and it is awesome. It's better than theirs. And the one you give credit to is our webmaster, Mr. Tom Totten. Now, if we could get him here, and I had 3 people booked and I couldn't find anything returning from the other one, but we won't even talk about him. I will say that I'm up here because President Jerry, well, I was going to say on assignment, but at our age, we're not on assignment. I'm sorry, I'm too old for that. But he is doing grandfatherly duties, and I sort of thought maybe he would be running scared that if he lost the election tonight for president, he would have a heart attack or something. Are we okay? Not that your picture's not, you're ugly, Tom, or anything. Past president. I'm also smelling freshly baked sourdough bread. That must mean Tom Whittemore is here. Tom, would you raise your hand so everybody can know that they can order their bread back? Former Westmont incredible teacher, had his own lab, taught science, retired a couple of years ago and is baking incredible bread. It's been a few years. Let me get my glasses out. We got stuff to do here. Thank you for coming. I hope I remember everything. How many of you in the audience now saw the show down at the planetarium? Raise your hand. I want to see. Okay, it's less than half of you. Because the auditorium holds, the planetarium holds what, about 35 seats. I'd like to see a planetarium that shows the night sky and then opens up like that moon base scene in 2001 Space Odyssey with the lemon fields, and you actually see the real, probably wouldn't see the same sky at all, would you? Not as much. So we're going to have our election in a few minutes. We're going to get to that and get right to it. Let me make sure I got everything. In-house members only, Dr. Farshad Barman and Sean Kelly, both doctorates. One's still practicing and doing very well. Whose students from City College are here to see their man for even more than just extra credit. And Farshad has, I think, a PhD in, what is it, electronics or engineering. Farshad, where are you? Okay, you're ready to go first, and then it'll be our gentleman that I've been waiting to see for a while. I've been waiting to see both of you. Farshad, you did a talk, did you not, years ago with Bruce?
Yes, years.
On the N-bodies, talking about, okay. I just want to really quickly, before we get into too much, there'll be something on the screen that collides with this or matches me, but we have a Monday morning podcast that's getting very crazy and very funny and very heavy. It's 11 a.m. If you have YouTube on your screen and you want to join us, if you want to just log in with us, you can do that too. We'll give you the link. It's 11 to noon. We're about to go into our 4th year. We're up to program number 198 every Monday morning, 11 to noon. It's called the SBAU Astro Hour. You can see us on YouTube just by punching those letters in, those words, SBAU Astro Hour. We're talking about things now like the Great Attractor. What the heck is that? Ooh. They think there's a 9th planet that we haven't seen. We're talking about that. The Penrose diagram. Somebody's actually mapped a black hole. Is that possible? Well, future speakers will be talking about it, I'm sure. So, weekly vlog. I got that out of the way. Silly science cartoons start every day. Recently, the three body problem. We'll talk about that too. Okay, without further ado, I'm going to follow along with Tom's notes and welcome you all to the SBAU 2025 officers election. We do have a proposed slate, and Tom came up with the idea because I was going to go one at a time. There's 4 offices open. President Jerry Wilson, who's been in office 7 years, since 2017, and myself 6 years. I came in his 2nd year. You know who I replaced? One of our youngest members. His name was Adrian Lopez, 17. He got yanked out on a scholarship at Caltech for free. Chose them over us. Can you imagine that kid? Sonny he was a good vice president too. We liked him. I think he's changed his major now. But anyway, I've been the vice president, unopposed so far, both he and I. We have something special going on in the secretarial part. We'll get to that because I believe Tessa is open to taking over our secretarial job. That has been really well done by Andy Allen. Incidentally, before we get into the vote, how many of you, first time, we would like to know, raise your hand if this is your first visit to our, okay, some of you are students of Sean, I know. Would love to get you on a regular basis. Any of you plan to go to our big meal next Friday night, a week from tonight? I want to get this out of the way too. Oh, okay, Sean's going to be with us. It's $40 plus 20 to join if you haven't. And I figure that $60 is about what you pay for a meal out of Lucky's on Coast Village Road these days. You get a whole year's membership. So, back to the screen. We do have a proposed slate of officers, president, vice president, unopposed, that's Jerry, who is not here, and myself, who's on the stage, secretary, and treasurer, been held for at least a year, I guess 1 year, by Pat McPartland, Chuck's wife, taking over for Colin Taylor a year ago. And since we did not make any rules about this, last-minute competition from unnominated SBAU members, is there anybody who would like to put their names up for any of the 2025 SBAU officer positions? Those 4. Secretary, treasurer. Oh, come on, give us a fight in this. Okay. Then otherwise we propose the following slate of officers. Jerry Wilson as president, Ronnie Herron for vice president, and I get to sub occasionally when he's not available, and book all the speakers, and incidentally I'll be telling you who's coming to town to talk to us over the next 4 months in between our 2 speakers tonight. So that'll be about a half hour from now. For president, our incumbent, Jerry Wilson. Vice president, yours truly. Treasurer, our incumbent, Countess, that's Tom's words, Pat McPartland. She definitely is. And for secretary, as the incumbent, Andy Allen intends to step down. Tessa Flanagan. All those SBAU members would like to have SBAU members only, paid up and ready to go, stand first. In place. Great. You guys are turning out. Very proud member here. Okay, if you approve of this slate as is, rather than going one at a time, raise your hand. Okay. Here are the approvals. Now, if you don't approve, raise your hand. You'll probably be kicked out. Okay, Andy, the rest of you can be seated. Thank you. That's it for the election. We're back. Okay. Ladies and gentlemen, next Saturday night, incidentally, that's the day after our big Timbers party out at the, that's where we have the Timbers. That's going to be an incredible meal a week from tonight. And then the next night, we're going to be gathered out here in the driveway up past Palmer Observatory. So, if you are ready, our first guest, I wish you'd worn the hat. But that's all right. Farshad Barman received his PhD in electrical engineering from UCSB back in '79. He worked in that field for several years. Farshad, oh, wait a minute, we're not, come on up anyway. Oh, no, sit down, because I forgot, we got the guys to bring up. I'm not used to doing this. Plus, my notes are all screwed up. So, without further ado, ladies and gentlemen, Pat McPartland, Treasurer and Merchandise. I'm sorry, it won't come out. Right, that's what Jerry does. Sorry.
Thank you, Ronnie. As you probably have guessed, if you are just new here tonight and wanted to see black holes, we're a club and we're running some club business before those talks. So bear with us, those talks will happen, and we'll just have some fun before all those talks. So I'm a merchandise manager, and I brought one of our tote bags up with me. It's a really cool bag. It has a pocket in front and has a zipper across the top and a couple of places that you can put water or whatever you want to put. I'm back with other items, those tables right over there. And so you're more than welcome to come on over and take a look and buy something.
Hey Pat, is that bag $100?
Well, for you, Tom, it's $100. For everybody else, if you're a member of the club, it's $25. If you're not a member of the club, it's $30. And then there's all sorts of other prices I've posted too. If you want to send me an email, if you're on Zoom, it's merch, MGR, @SBAU.org. So back to you, Ronnie. Thank you.
Farshad, we will do your introduction again. Just sit tight, trust me. I was told to speed it up, hurry, and right away I'm getting to the main attraction. These are things that are definitely needed. Free reports. This woman you just saw is married to the most incredible man in the world as far as astronomy, as far as I know. He's the heart and soul of the club and the man behind your planetarium show, Chuck McPartland. In Santa Barbara Astronomical Union.
Oh, keep the microphone in front of the laptop. Move the microphone back in front there.
Okay.
Thanks.
Okay, thanks, Ron. Okay, quiet month. We had a school last night, Aliso School Din in Carpinteria. But otherwise, all we've got scheduled for this month is our regular event, second Saturday here at the museum. So that's the 10th, next Saturday, weather permitting, starting at 7. And then we have, December 10th, before that, we have Telescope Tuesday. So second Tuesday of the month this year. But for next year, we try to make sure we have enough moon to look at, because it's a commuter rail marketplace and there's a lot of lights. So next year we'll be moving, starting in January, we'll be moving to the first Tuesday of the month, just to warn people. And then third Friday of the month is always Westmont College Public Telescope Night. And they got a nice big 24-inch reflector in the dome. So it's pretty much just the vanilla version of outreach. And pardon me, I've also got a notice from the Night Sky Network that their pins are ready, so we'll be ordering pins for people who did a lot of outreach this year. And there's propaganda down here that you can grab on the way out. Star maps, moon maps, webpage listings, bookmarks, stuff like that. So thank you.
Thank you. As you're walking away, Chuck, did the Aliso School thing happen, or did you get washed out? It did.
Oh, it was timed out, but we still went down and gave a presentation.
Because that man I ran into last night that was complimenting Tom on the website, I was headed there, and I guess they didn't go or something. I said, I don't know, but sometimes.
Yeah, we were timed out, but we didn't do telescopes. We did rocks from space. We hit them with meteorites.
All right, thank you. If you haven't gone through the incredible 5-pound meteorite shuffle that he does, we've got to get a name for that 5-pounder that will make your feet walk like a duck. That'll be next Saturday night. Bundle up. Okay, ladies and gentlemen, I thought maybe I'd give Andy a chance after you. Okay, let's bring up Diane, and then Andy wanted to say something because he's now stepped down, and I'll have you after her. Diane Wilson-Beck, Events Coordinator. Ladies and gentlemen.
Hi, everyone. Our last event for this year is going to be our year-end holiday party, and it's for members only. So like Ron was saying, if you're not a member, now's a good time to join. it'll be for next year, your membership. The cost for this event is $40 per person, and it'll be held at the Timbers out in Goleta. It starts at 5 p.m. with a lovely slideshow of astronomy. Then we'll have a buffet meal, and then a white elephant gift exchange, which will be a lot of fun. So anyway, you've got until December 8th to sign up and pay for the event, and we're hoping that all of our club members will consider attending. Thank you.
And ladies and gentlemen, our outgoing but very well received and a great job he did, Andy Allen, secretary, wants to come and say a few words.
Hello, so for the first time in 12 years, we have a new membership directory. So this is a directory of people who are members of the club who have specified that they do want to appear in the directory, and it has only the information that they've said they want in the directory. So for some people it's just email, for others it's just phone, and so on. And so these are, there's print only, we're not making an electronic version of this. And we also ask that people don't make an electronic version of it, so we kind of keep it in the family, and it's just for members only. So if you're a member, then you can buy one for $1. So if you're interested in getting one, come and find me. Thank you.
Can I have that one you just showed everybody here? Thank you, my friend. Tessa, the new secretary, would you like to say a few words? Where are you?
No, everybody knows me. I'm here. I'll be secretary. If you need anything, let me know.
And I think I can get away with saying this. If you want to go on the screen with us when we do that second Saturday, 4:30, possibly moved up to 4 p.m., our planning meeting, which is like a board meeting. There's 6 or 7 of us on the screen. It lasts about an hour, hour and a half. We'd love to have you on. You may be watching a lot, but you can certainly comment if you want to. I think we're done there. So check with people after the show and mingle, buy some stuff off the table, pick up your freebies. Now let's meet Farshad and Sean. Mr. Barman received his PhD in electrical engineering from the university, 79. I think that's right. Is that right? 79? Yes. Because I make my 9s look like 1s sometimes. After working in that field for several years, Farshad Barman then got his master's degree in mathematics and even taught math at Portland Community College until his retirement in 2015. He and his lovely wife, who he's seated with, I believe, you spend summers up there. He just came back to town for the winter months. And his research has been in mathematics of astrodynamics. Woo! Tonight, it's called Simulations of Near Stars Orbiting Sagittarius A, but his wife came up with a better name. What was it? Hitchhiker's Guide to Sagittarius A or something like that? To the galaxy. Ladies and gentlemen, Farshad Barman.
Hello everybody, my name is Farshad Barman, and if Tom will be kind enough to get my...
Just, you go ahead and share your
share
PowerPoint.
screen.
Share.
Wait, share screen. Is that what I do?
Your slideshow. You might have to go down, maybe. You might have to go down half page. Try that little bar on the right. Yeah, not there. Huh? Where's your PowerPoint? What happened to it? It's not the media player, right? It's not that, is it?
It's
Oh, maybe.
not doing anything.
Well, you have to click share in the bottom right.
Well, he hasn't chosen the.
Oh, yeah.
There you go. There you go. Is that it? Or is that your math one?
I think so. Let me see. That's not it.
It's stop share.
Stop share.
And then hit share again. Let's,
Hit share down here.
right. And
So I
what,
have a,
You got a couple more
PowerPoint.
windows if you scroll down.
yeah, I didn't
I'm scrolling down.
Didn't have, oh, show all windows, click on that, show all windows.
Oh,
No,
there it is.
there it is, all right.
Here it is. Okay, got it. All right, I have my email there for you if you have any questions. You're welcome to send me an email if you'd like me to send you some of these programs. I'll be more than happy to share them. The title of my talk, A Hitchhiker's Guide to the Stars Orbiting Sagittarius A and Their Possible Planets. Those of you who are old enough and remember the book, Hitchhiker's Guide to the Galaxy, anybody remember that? Okay. I took the title from that because I'm going to actually take you for a trip around the galaxy tonight. And I will bring you back home, don't worry. And we will be taking a look at the stars around the black hole at the center of our galaxy. Okay. And again, I took this quote from that book. You just come along with me and have a good time. I hope you will all have a good time going around the galaxy on this trip with me. Okay, our Milky Way galaxy is a barred spiral galaxy. There's a central bulge right here, and the bar refers to this long extension of central stars, mostly older stars. There are two major arms that come out of the end of these bars. This one is that the Perseus arm? One of them is the Perseus arm. And this one, if I remember, is called Centaurus arm. And then there are smaller arms and spurs. The sun is right here, about halfway from the center to the outer edges, out in the suburbs. It's near a spur called Orion Spur right here. I'm going to take you for a trip when we are ready around the galaxy in this direction. First, we will make a stop right here. Then we'll make a stop right there. Then we'll stop right there and take a look. And then again, as I said, I'll bring you right back home. All right, this is a picture of some of the stars orbiting the black hole at the center of our galaxy. This was published back in the 1990s for the first time by the UCLA Galactic Center group. They were taking these pictures by an infrared telescope. Infrared does cross or pass through all the dust and the dirt that there is in our galaxy between that black hole, Sagittarius A, and our solar system. And they noted the position of these stars every year from, in this picture, from 1995 to 2008, about a 13-year period. I'd like to bring to your attention 3 or 2 stars right now that I will be talking about. The red one right here, oops, sorry, right here, is called SO2, the name of that star. It's approximately 10 to 15 masses of our sun. And the way they display the motion of these stars, they start with a light-colored red, very light, and every year they record the position and they note it as a darker red. It moves and finally becomes a dark red dot right there. So to give you kind of direction of the motion of these dots. So SO2 starts here in 1995. 1 year later, it moves a tad bit. Another year later, a tad bit. And as it gets closer to Sagittarius A, which is right here, notice in 1 year, it moves quite a bit. And in another year, it moves quite a bit more. And then a little less and less. And as it gets farther from Sagittarius A, it moves even less. What law does that describe? Does anybody know? Huh? Right, that's Kepler's second law of planetary motion. That says, just to put it very easy to understand, a star goes faster as it gets closer to Sagittarius A, and it slows down as it gets farther away. Equal areas in equal time, sometimes it's known. The planets do the same thing as they orbit the sun. In fact, any object orbiting another much heavier object does the same thing. The other star is SO16. That's right here, the kind of a turquoise color. It starts right here in 1995, moves towards Sagittarius A, and right there it gets real close to Sagittarius A and moves in that direction. Its orbit looks really elongated and narrow ellipse. And I'll talk about these different shapes of these orbits in just 1 minute. Okay. By the way, just to give you a scale of this picture right here, solar system looks like this dot right here. That would be the orbit of, I included Pluto. Orbit of Pluto would be about that black dot there approximately. So these are huge orbits, big, massive orbits. Okay, I'm going to give you a couple of words because I'm going to be using these words as I show you the slides. When a celestial body orbits another much heavier body, its orbit is an ellipse. The heavier body is in one of the focal points. And when it orbits, the closest point of approach is called periapsis. The farthest point is called apoapsis. If we are in our solar system, we have a planet orbiting the sun. We call this one perihelion, and that one aphelion. And if it's the moon orbiting the earth, what do we call this shortest approach? Perigee, thank you, Sean. And that one, apogee. G meaning, or geo, the Greek word for earth. And perihelion, helio, the Greek word for the sun. So for any other body orbiting another one, periapsis, just remember this one. Periapsis is the closest point. And one other word that I'd like to mention is eccentricity. That gives you the shape of the orbit, which is usually an ellipse. If the eccentricity E is 0, it's not eccentric at all, that orbit is exactly a circle. If eccentricity gets a little larger, closer to the number 1, it becomes an ellipse looking like this. And if it gets even closer to 1, it becomes a very narrow, long ellipse. So when I talk about eccentricities, when I say an orbit is very eccentric, it would look like this. And not so eccentric, it may look like that. Okay, so I have done a couple of different simulations, and I will show you the pictures of all these. The first series of simulations I've done with a math program called Maple, and that one draws the orbit and places the star where it should be on the orbit at a given time, let's say 2008. The drawing of the orbit is real simple. The ellipse in mathematics is defined real nicely, and then rotating this ellipse in 3 dimensions to make it oriented exactly the way it is also easy. But locating the star on that orbit takes some mathematical gymnastics, and I'll show you that in just 1 second. The second series of simulations that I've done are by the program Python, which is a free program you can download. And lots of mathematicians and astronomers use this program. Its simulations are n-body numeric simulations that I've done. I take a planet, I put it around the star, and make the pair orbit the black hole to see if that planet will have a stable orbit, whether that star will be able to support the planet. Okay, this is my only slide with mathematics in it, so promise me that you won't want that. I will just spend 2 minutes describing the mathematics of these simulations just for those who are interested, and then I will show you pictures with very little mathematics in it. The Maple simulations start with what we call the space curve, which is the shape of a orbit. If you take your finger and go like this in 3-dimensional space, you're describing a space curve. It's described by x, y, and z of t, the directions, 3 directions. To start with an ellipse, all you have to do is A cosine and B sine, which are the building blocks of an ellipse of a given time. And in the z direction, I'll make it 0, so the ellipse right now is on the xy plane on the floor. The argument of sine and cosine is what I mentioned are mathematical gymnastics. Bessel solved Kepler's equation that describes that motion that we mentioned, speeding up as it gets closer to the black hole and slowing down, and came up with an infinite series of terms, including Bessel functions that he developed to describe these J sub n's or Bessel functions of the nth order. I only need to use the first 50 terms for very accurate description. Then I multiply this space curve by 3 matrices to do the rotations. So I take that ellipse that's on the floor, rotate it one way, rotate it another way, rotate it a third way, and it would be in 3 space exactly the way it should be. The second series of simulations that I did by Python are n-body simulations, and that I used Newton's law of motion, the second law of motion. F is ma, most of you remember that from your physics classes. And then the gravitational force given by this, you equate these to come up with a differential equation, second order differential equation, very nonlinear. Break it up into the x, y, z components. So you have 3 equations for each body. And if I have 3 bodies, the planet, the sun, the star, and then the black hole, you have 9 equations, a system of 9 equations, all interrelated that you have to solve. And I used the Runge-Kutta technique, Runge-Kutta, 4th order Runge-Kutta. And I'd like to mention, when I wrote this, I was working with Bruce Murdoch, who's here, And he gave me quite a bit of help writing this program because he had already done that himself. So I give him credit for that. Okay, I'm done with math. Nobody walked out. That's good. All right, these are the stars that I worked on and did simulations. I used 10 stars. SO16 is that very eccentric blue orbit that I showed you. SO2 is that red one, my favorite one, in fact. I really enjoy the simulations of SO2, and the reason is when I used to teach at Portland Community College, I would use this star to give projects to my students as application of mathematics in astronomy and had them do the simulations with the equations that I showed you. The farthest out star that I studied is S66. And here's the distances, the periapsis distances that, again, are the closest approach to the black hole. SO16 gets within 56 astronomical units of the black hole. That's a little farther than Pluto to our sun. So it's really close. For the black hole, by the way, is 4 million masses of the sun. So it's a monster sitting there, and getting that close is pretty brave. SO2 comes within 118 astronomical units, a little more comfortable. And the farthest out one is 10,700 astronomical units, way, way out there. But I will tell you when I get to the point, which one of these is able to have planets. The ones that are very close, just to get ahead of myself a little, the ones that are real close won't have many planets, if any. The one that's way, way far out will have a full-fledged solar system-like planet system. And these are the orbital periods in years. SO16, that blue one, takes about 55.3 years to orbit. SO2, my favorite, about 16 years. And the farthest out one, S66, about 664 years to orbit Sagittarius A. Okay, I'll show you 3 slides of my orbital simulations using Maple. SO2, the red orbit. Sagittarius A is sitting right here with the black square. SO16, the eccentric one, comes within about 56 astronomical units. SO20, SO19. Another one that I'd like to bring to your attention is SO38. This one has what I've drawn as a gray orbit. SO38 comes within 218 astronomical units of the black hole. So when we go for our trip around the galaxy, I will bring to your attention the position of these stars so we can see a 3D picture. By the way, these are all 3D pictures. And if I go back for one more view of this slide, what we usually see right here.
So you want to reshare the Maple programs that you want to do?
Reshare.
So stop share of the PowerPoint at the top.
Stop share.
And then open up your Maple program. And share screen.
I'm not there yet, Tom.
Oh, you're not? Okay.
No, I just wanted to show that slide. Where am I? Here. No, here. Okay. Let me do this. No, this is not where I want to be. I want to be right here. Okay. This slide that I showed you, these are two-dimensional pictures, of course. They take a look at the stars with their telescopes and give us, we don't really know how these are oriented, these orbits. So one of the purposes of my simulations is to give you a three-dimensional picture. So let's go, there we go. Now, how do I get this to go to full screen, Tom?
You start your slideshow.
Stop share.
Then that'd be okay at the top so you can see more.
Okay, at the top.
That blue square, it says okay, click that on.
Yeah, but I
Then
want to.
slideshow.
I want to go
Slideshow
over
at the
this
top.
slideshow. I see it right here. Okay. Now, let's go zoom out and take a look a bit more of all these stars. SO2, the red one, SO16, the blue one, SO38 is the third one that I'd like to bring to your attention. When we go traveling around the galaxy, I will keep asking you to keep track of these three stars. It would be really nice to keep track of these three as the orientation we go. And if I zoom out a bit more, I see S66, the one that was the farthest. That was about 10,700 astronomical units from the black hole. So let me go back here. This is a 3D picture, and I'm going to show you, this is the time where we are going to go for our trip around the galaxy. So if I want to go to my Maple program, do I do stop share?
Right. And share. If the Maple program's already open, then you can just do share screen again and
Share screen.
find the Maple program.
And find Maple program.
Scroll up a little. Maple was up. There's Maple.
That's not Maple.
Let's stop share that one.
Stop share.
And share screen. If Maple's already open, you might want to go to Maple, see if it's already running. Yeah, find Maple.
There's my Maple.
And,
Okay.
but now you have to go back to Zoom and share that. Find the Zoom.
Back to Zoom.
Go back to Zoom, which is right here.
Under
Screen.
Share screen right down here.
Look
Right.
at the little maple icon. You see that icon with the maple leaf? It's on the left-hand side.
This
That
one.
yeah.
Got it. Okay, thank you. All right, we are ready to do our trip. All right, we are starting at where the sun was, and I'm going to go counterclockwise around the galaxy in a circle and return back to Earth. If we were traveling with the speed of light, that would take about 170,000 years. But I'm going to take you faster than the velocity of light and maybe take about 170 seconds. So let's see if we can do that. All right, again, keep track of these three stars. SO2, the red one, SO16, the blue one, and SO38, the gray one. Okay, we are a quarter of a way around the galaxy going counterclockwise. There's the blue one. It's not quite as eccentric as it looked in that very first picture. Now notice SO38 is almost edge on. so you don't see the orbit. It looks almost like a straight line. Okay, ready to go to our next stop, which is the far side of the galaxy, 180 degrees around. Are you all ready? Okay, let's go. Okay, I'm a little tipsy here. All right. Now we are on the far side of the galaxy, 180 degrees around the galaxy, and looking at these, notice that blue orbit is to the right, SO2 is still there, and SO38 is to the left. So it's kind of like a mirror image of what we saw before. And if we look far enough straight ahead, we will see our solar system, right? If you're 180 degrees around, look down at the solar system. But it's hiding behind the black hole, of course. Okay, one more 90-degree turn, that will be 3/4 around. There, we are 3/4 around the galaxy, taking a look at that picture. Again, SO38 is almost edge on. And as I promised, I'm going to bring you right back home. There, our original position, the solar system, we are safely back home. Aren't you happy we're back home? Okay. All right, now I want to go to my
Back to PowerPoint.
Share again.
share again.
Stop share.
Stop share again.
Stop share. Okay, and then I go.
Go to share. Go back to share screen. Go up. Yeah, go up with your arrow. Yeah, share screen.
Oh, here, share screen.
And find the PowerPoint.
PowerPoint. PowerPoint.
What is it? Guess it's getting the one back up at top. The one with the P on it, the icon has a big P on it. Go up. Not sure.
I'm not sure if I.
Go back up. With the one on the right, with the P, is that it?
This one. Got it.
And then
Okay.
start slideshow somehow.
Slideshow.
Resume. Oh yeah. There you
Okay.
go.
Now, let's go to the other set of simulations, the Python n-body simulations. What I did to figure out whether any of these stars could support a planet is I took a planet, placed it in orbit around the star, and then let the pair orbit the black hole. The examples I'm going to use is just with that star SO38. That's the gray orbited star. First, I put a planet about 0.38 astronomical units from the star. That's about as far as Mercury is from our sun, real close. And I let the pair orbit the black hole. And it seems to be working, and the star or the planet seems to be staying in orbit around the star. By the way, I exaggerated the vertical axis just to show the slinky of the orbit of the planet. So the planet is orbiting the star, and the star is moving, orbiting the black hole. Somebody tell me, why does the slinky look stretched right here and not as stretched here? Anybody know?
The speed of the planet.
The speed of the star and the planet that's following the star. So the star is orbiting the black hole, and the star speeds up as it gets closer, and the planet keeps following the star, and its orbit looks like a stretched slinky. So I decided that SO38 could support a planet as far as Mercury. And I take a look at the orbit of the planet around the star as the star is orbiting the black hole, and its orbit looks pretty stable. It's an ellipse and it keeps going around and around. Then I put a planet about as far as Venus is from this star, 0.72 astronomical units, and take a look at its orbit. And notice that the orbit of the planet, which is the blue orbit here, is really wobbly. The planet goes back and forth, but it stays in orbit. And I decided that because it takes about tens of millions of years for a planet to form, the debris around the star that would have been a planet at Venus's distance would not form. So I decided that SO38 can support a planet as far as Mercury but not Venus. Then I put a planet as far as the planet Earth around the star, the same star, SO38. The planet starts orbiting, and you can see the slinky stretch, and it stays in orbit the first time the star approaches its periapsis, and it stays in orbit. The second time the star approaches its periapsis, the planet leaves the star and starts orbiting Sagittarius A instead. You see that blue line? The planet leaves its host star and orbits Sagittarius A. It's as if Sagittarius A says to the planet, "Come orbit me, I'm more attractive gravitationally than your star." And the planet obliges. So I put all these together. This is, by the way, before I show you my last two slides, this is the orbit of that planet at 1 astronomical unit where it leaves. The first time it's orbiting really nicely as around the star in an ellipse. The first time that the star approaches the black hole, it becomes tipsy. The second time, it leaves right here. It leaves and goes and orbits the black hole. Okay, I'm ready to show you my results. On the vertical axis, the x-axis, I have put these stars that I have studied. SO2 comes within about 118 astronomical units. On the vertical axis, I have shown you the planets that it could support. SO2 is too close. It won't have any planets. This is, by the way, the black hole at the origin. SO38 comes within almost 200, or a little more than 200, 218, I believe, astronomical units. That's the one that I showed you the simulations. It will have a planet as far as Mercury, but no more. SO4 is about 650 astronomical units, its periapsis. It will support a planet as far as Mercury, one as far as Earth, and one as far as Mars, but no more. By the way, you notice that the closer in the planets, the tightly bound they are to their star, so they're not as easy to be stolen. But as they go farther, the planets, they can be stolen by the black hole. This one, S42, is about almost 3,400 astronomical units, as close as it gets to the black hole, and it could have a planet as far as someplace between Jupiter and Saturn, but no more. And then the next planet shows the very last simulation. S66 is the farthest one that I simulated. It's about 10,700 astronomical units to the black hole at its closest approach periapsis. It could support planets all the way to Neptune. So it could have a solar systems very similar to ours. So you have to be about 10,000 or a little more astronomical units to this black hole before you can have a planet as far as Neptune. And that's about what I have for you. And as I promised you, I'll bring you home. And I hope you enjoyed the trip around the galaxy. Any questions?
I have one.
Yes.
Not much of a Goldilocks zone around the old big black hole, is there?
No, the Goldilocks zone is way out there.
How in the world do you get these things? They're having trouble finding and photographing the red ring around the black hole itself. You're talking planets already? How did you get that?
Simulations, you can do whatever you want.
So you made all this up, aren't you?
By the way, because, in fact, not only did I make it up, it takes about 27,000 years for the light from the black hole and its stars to approach us. So everything I've told you is almost all totally outdated by 27,000 years. I made them all up, right?
Any other questions real quick? Something you're just gonna lose sleep tonight if you don't get it answered? Bruce, you wanna stand up or raise your hand, your partner in this crime? There he is. Part of the crew on Monday morning on the astronomical
Oh,
unit.
yes, yes. Should I remove this?
I'm not sure. I mean, there's a little break as I speak about what's happening. Are we ready to go with Sean?
Yeah, you can stop share.
Can I
Stop share.
Stop share.
stop share?
Stop share. Oh my God. That's a great picture. The one the astronauts took on the first, second, and third last Apollo.
Okay, stop share. And am I ready to pull it up?
Yeah, I think so.
Okay.
Sean's up, I guess.
All right, my friend. You know, share the stage with me while I thank you, Farshed. Oh, Sir Farshed, before you go. Our official priceless ceramic cup for your duties. Let me just quickly tell you that you're going to be experiencing what a lot of his students experience, I assume, in the next half hour or so, up at City College, where he'll tell you how long he's been in charge of the astronomy department up there. A month from today, a little less than January 3rd, Dr. Damian Christian will be here from Cal State Northridge. His talk, Exoplanet Research Techniques and Discoveries. February 7th, UCSB postgrad student, a new PhD, Dr. Shamindu Amarasingh, takes us down a 1-mile deep shaft at a former mine in the Black Hills of South Dakota for a riveting tour of a continuing experiment to find dark matter. They're looking for WIMPs. I think they're using frozen xenon or liquid xenon. So March 7th, back to exoplanets with a twist. Get this. Renowned author and astrophysicist Dr. Jeff Bennett, who's coming to town anyway that weekend, and I got him to the museum because he's going to do some other talks around town and at the museum, and I got him for this. He's coming from Colorado to host a talk he calls Beyond UFOs, the scientific search for extraterrestrial life and its astonishing implications for our future. And Farshad, you're going to want to come back for sure in April 4th, the return after a couple of years of that young rising astro star out at UCSB and LCO. He works for both, Dr. Joseph Farah, a young man who gave the talk last night. An update of what he told us earlier. He was involved in taking the first photograph of our black hole. They took one on another galaxy before. This man knows it all. Anyway, that'll be Joseph Farah again on April 4th. Right now, let me tell you quickly about Sean. The wondrous White Dwarfs. He has some as pets at home. A BS in science, a lot of BS on stage. BS. Wait a second. We're going to have a food fight with him.
Yeah, PhD for science.
I know you are. I can't wait to hear your speech. He's got his science degree, BS from UCSB in physics, and MS in physics from New York University, PhD in experimental solid state physics, graduate school, and University Center CUNY, which City University, okay. I assume that would be your thesis and dissertation?
Yeah.
Okay.
You can read it, it's online.
All right, morphology and photocatalysts of titanium dioxide. I'll let you tell them.
Okay, you got it.
I can't wait.
All right, here we go.
I'm telling you.
Okay, so there you go, Tom. All right, good. I'm going to share it. I think we're going to get this going real quickly here. Let's see if we can make this work. If we're lucky, it's all going to work perfectly, right? Everything works perfectly, right? Look at that. Is that right? Oh, my goodness.
Yeah.
You guys want to hear my voice?
Yeah.
Or do you want to see? There's the text down there. Anybody into that? Sometimes that was cool. You know, back in the COVID days, anybody remember those days? The good old days. Oh, oops. I just bumped something. You're going to come back?
Give it a minute, maybe. Maybe.
Okay. Hold on, one try again. Let's try it again. Never give up. That's how you get a PhD. There you go. Is that good?
Yes.
Tom, do you see it shared?
I see like the PowerPoint.
That's right. Share screen. Share screen. We're going to go to the presentation. Oh no, how about this? We'll do this. Oh, do you want to do, yeah, either one, right? Or you want me to do?
Just want to see
What do
your,
you want me to do?
share
I'll
the
do this.
slideshow.
Let's try that. Does that work?
Yeah.
Okay. All right, everybody ready? Okay, so wondrous white holes. No, white dwarfs. Sorry about that. That was a joke. Sorry. Anybody know what white holes? We're not talking about white holes tonight. We could have talked about white holes. Anybody want to talk about white holes? Okay, how many have we seen? That's a good question. All right, so I actually got a little help. Has anybody played with ChatGPT yet?
Yeah.
Have you played with it? It's kind of cute. I don't know if I advise you, but I think it's actually a pretty neat tool. Let's see if this is working. It's not quite working. Okay, well, I have to stand here anyways. I'll just use my mouse. Let's see if it works. There we go. Oh, that's why. Okay. So this is actually, I asked ChatGPT to generate a picture showing a white dwarf and all the discoveries of the last 100 years. You can see this is actually like this futuristic lab where we have, we're studying everything, around the universe. I'm not sure.
Can you tilt your screen back?
Sure, tilt your screen. You're looking at your name tag, Sean, not your face. Okay. All right, there we go. And I thought that was kind of cute, pretty cool. Actually, you can generate a limited number of things with a free account. I didn't pay for it, so I used a free account. And then I don't know why. What do you got?
Use the arrows.
I know. Yeah. Okay, we'll try that. Oh, there it goes. What is a white dwarf? Hey, we're going to start off easy, everybody. So I have a few things I'd like to talk about. Where do they come from? A little bit about what they're made of, right? And then to talk about what's really remarkable about them. I don't think many of us understand how strange and exotic white dwarfs are, right? They're really exotic matter. And then, of course, the fun part is when they have a companion. What happens then? They get to do a lovely dance together. Oh, it's working. Wonderful. Okay, so this is just a brief definition so everybody knows what I'm talking about. A white dwarf is a core left behind by a star at the end of its life after it's exhausted its nuclear fuel. Okay? And actually, the only thing left of the star is really the core. It's expelled all the outer layers of the star and forms something called a planetary nebula. You get extra bonus stuff. We're going to talk about planetary nebulae as well. So just a little trivia for those of you who like trivia. What's the name of the brightest star in the night sky? Anybody know?
Sirius.
Are you kidding me? Right, there you go. Some of my students know what I just did. So Sirius, yes, Sirius. And there, if you look very carefully down below, you see the little white dwarf, the companion to Sirius. So now, tonight, when you look at Sirius, I want you to remember that is the closest white dwarf, 80.6 light years away from us. Isn't that cool? Now, not all stars will become white dwarfs. What do you need to be if you're going to be a white dwarf? You need to be kind of small. So this is our flow chart. Actually, some of you have probably seen this before. This is a great slide on Wikipedia. You start off with a big cloud of stuff, right? And something causes it to collapse, probably a supernova, and then the star is born, right? The star is born, but it has different pathways it takes depending on the mass of the material that is present. So the path that we're going to talk about is a low mass star, which means that it's less than 8 times the mass of our sun. Okay, so if you're more than that, you're probably not going to make a white dwarf. You're going to make something a little more exotic, like a neutron star or a black hole. And you are also going to supernova. Now, the interesting thing is white dwarfs get to supernova too, but kind of in a special way. So we're going to take this branch down here, and we're going to see that we're going to take a low mass star. It's going to evolve into a red giant. Those are enormous stars. Yeah, question?
Can you unmute yourself on Zoom?
Turn down the microphone?
Turn the microphone on the Zoom screen. Yeah.
My mic is not on. Okay, here we go. Let's see, how do I unmute myself? Is that better?
Yeah.
Okay, sorry about that. Sorry, people at home. I'm just looking at pictures and not hearing any of my good jokes. Okay, so the red giant stage is actually where it's going to eject layers of itself. So we'll talk more about that in just a second. Once in a while, you're going to have stars that have a companion. And so that's kind of a different story that we really want to talk about. But if you just have a single star, you're going to see what forms is something called a planetary nebula. That's a quite beautiful thing. And in the middle of that planetary nebula is a white dwarf. And if you wait long enough, how long is this? This is actually really interesting. I don't know the exact time right now, but I can tell you it's a long time. Anybody know? Trillions of years? Billions. It's something like trillions of years. Okay. Now here's just kind of a fun little story. This is just a picture. I took it from NASA here. But you can see our sun is born, it evolves into a giant star, and then the very last thing it gets to do is be this thing called a planetary nebula before it dies. Okay, and then it'll be a white dwarf. So there actually is a lot of life left in our sun. Here's where we are right now, about 4.6 billion years, and we've got another 5+ billion years before the hydrogen in the core runs out. Right now, the sun is doing core burning of hydrogen. So the hydrogen, everybody know how this works? The hydrogen is fusing into helium in the core, and when that runs out, that will be the end of its main sequence stage. So it stops being a regular star and turns into this thing called the red giant. So again, just a brief thing. I didn't want to bore you with lots of complex fusion diagrams. Although, who would have liked to see fusion diagrams? Anybody? Okay. Yeah, I actually was contemplating about it. I wanted to talk about it a bit. But basically, the sun right now is doing this hydrogen core burning. So the hydrogen is converted into helium. And actually, you're not my students, but you need to know this. Are you ready? There's going to be a quiz afterwards. If you are hydrogen and helium, right? The hydrogen is the fuel, and the helium is what is made by that fuel. There's a number one principle you need to understand, is which one has more mass, right? This is the number one principle. Who knows the answer? Is it the hydrogen? Raise your hand, hydrogen. Raise your hand, helium. Okay, so unfortunately, most of you got it wrong. That's interesting. So what you need to know is that the hydrogen mass is greater than the helium. And every time fusion takes place, a little tiny bit of matter is disappeared. It disappears. It's gone. Well, it's not exactly gone. It's converted into other forms of energy. And this is how stars work. Who knows the famous equation? E equals mc squared. That's how it works, right? The matter turns into energy that powers the star. Okay, so the helium is forming in the core. It's not fuel, right? Why isn't it fuel? Well, it turns out, I don't want to give you a bunch of numbers, but anybody interested in numbers? It takes about 10 million Kelvin to start fusing hydrogen. And the reason why is hydrogen is basically the proton and another proton, and they don't like each other because they're both positive. So when you form helium, it turns out it's even worse because helium has 2 protons. So 2 protons and 2 protons really don't like each other. And so the fusion requires a temperature of almost 100 million Kelvin. That's a big jump in temperature. So after we run out of the hydrogen in the core, we can't really do fusion for a while, right? There's not going to be any fusion in the core. So the core begins to contract. And those of you know a little bit about science, what happens to a gas or a plasma when it contracts? It heats up. It begins to heat up. And so this beautiful core, which has been doing all the work for the star, can't do it anymore. It just contracts. And the area outside the core finally reaches this critical temperature, 10 million Kelvin, and all around the core you get fusion. It's called hydrogen shell burning. Wow, this is exciting, right? Isn't it cool? So our sun is actually fusing hydrogen much more than before, and this causes the star to blow up into a giant star. So you guys might know this. Mercury, anybody know this? Is going to be inside of the sun. Venus is going to be inside of the sun. Earth, probably inside of the sun. Mars, we think, is going to escape. But this is that's a pretty important part of the sun's life. So it's after its regular lifetime that it starts to do this. And now the helium will eventually begin to fuse. That core will contract, and eventually the helium becomes a fuel. Anybody know what a helium particle, a nucleus, is also called? Some of you might know this. Another name? An alpha particle. If you've never heard that before, that's a cool term, right? And a helium nucleus is an alpha particle. The helium fuses in something called the triple alpha process. You can figure this out, right? You've got 2 protons, and it takes 3 of them, right? What do you make? 3 times 2 is 6. You make the element carbon. Now, sometimes some of that carbon will actually grab one more alpha particle. You'll make a little bit of oxygen as well. So the core becomes carbon with a little bit of oxygen mixed in. And meanwhile, this giant red star is ejecting layers of itself away. And eventually, there's nothing left. And so that tiny little core, which is carbon and oxygen, is going to collapse. And we think that our sun is probably going to about half of its mass will be left by the end of its life. Okay, about half of its life. So this is just a fun, pretty picture. You know, look at this. Isn't space beautiful? Really? It's amazing. These are planetary nebulae. So once upon a time, we thought they were planets. They're not. But they are the remnants of these red giants with their shells of material expanding away from the star. And in the center, what's the power that's lighting them up? It is a little tiny white dwarf. Okay, so the hot white dwarf is located in the middle. Sometimes you can see it, mostly you can. And that thing is emitting ultraviolet light because it's very hot, and that causes these gases to glow while they're close. When they drift far enough away, it's going to fade away. It's only about 1,000 years, 1,500 years, something like that. I just, again, throw a question out. I think this is really cool. Some of my students know what I'm about to say. You see these spherical shapes, right? But you also see these elongated shapes. And I think that's kind of interesting. So if you have any idea, anybody have an idea why you might have these elongated shapes, these shapes that show kind of jet structure? Anybody have an idea? A magnetic field. There's a magnetic field probably, right? A magnetic field can be generated if there's a companion to the red giant. So the companion star can do that. And so in some of these cases, it's pretty obvious that something like that is going on. Okay, so I want to tell you about these things, these white dwarfs. They're pretty exotic. So put your hands together. There you go, thank you. I'm asking for a little applause earlier. So when you put your hands together, I know you feel how solid your hands are. Don't you feel how solid? Everything is solid, isn't it? Everything is solid. And it turns out, this is an interesting thing we learned about in physics. It's the electrons that make atoms feel solid, right? The clouds of electrons that surround every nucleus are what are interacting when atoms touch each other. So the clouds of electrons repel each other when they try to get close. That's what you're feeling when you put your hands together. The clouds are actually repelling each other. So there's a couple of principles. Some of you may know them, but I'd like you to be aware of them, and I don't have them yet. But we're normal matter, right? We've got these nuclei with the electron clouds around them, and we're not very dense. This repulsive force of the electrons is what keeps the atoms from kind of joining together. They stay apart. But what we're going to talk about with white dwarfs is electron degenerate matter. This is exotic. And it turns out it's mainly these positive nuclei with a whole bunch, a sea of degenerate electrons that are not bound to the nuclei. And that's the key. This is probably one of the most difficult parts of understanding white dwarfs. It's not normal matter. It's really strange. And so the electron repulsion that we feel when we put our hands together is not enough, actually, to support the white dwarf against gravity. That's a key piece of what you want to understand. So how does it work? Okay, so a couple of principles, and I don't want to bore you. These are amazing principles, so if you don't know them, just take a quick look. There's something called the Pauli exclusion principle. It says that no two fermions, we don't have to be fancy, we're talking about electrons right now. Okay, so no two electrons can have the same quantum state. And this is really a neat thing if you've ever studied chemistry and how you build the electron clouds. When you put the electrons onto an atom, there's a limited number that can be in the closest level called the ground state. Once you build that, you have to start putting them in higher and higher and higher layers. So the larger the number of electrons, the larger the cloud of electrons will be around that atom. Hopefully that makes sense. That's the Pauli exclusion principle. What we see happen inside of a white dwarf is the electrons are going to repel each other and produce a kind of pressure. So we call it electron degeneracy. Well, it's going to be electron degeneracy pressure in a second. Okay? But there is another thing that I think you should understand, and that's called the Heisenberg uncertainty principle. And so I asked ChatGPT how to explain this, and they gave me a couple of versions. This one is kind of intermediate. This is not super high level, but it's intermediate. And the idea is that when we talk about the position, that's x, or the momentum, that's p, we talk about how carefully we know the position of the momentum, and this symbol delta is the uncertainty. So it means how well do I know the position, how much off could I be, right? So if I know something is located between my hands, this would be considered the uncertainty in position. And so it turns out something really bizarre, but built into the universe, built into the fabric of our universe, you can't perfectly know both of these. If you try to really confine something and know its position very well, it turns out that it starts moving faster. We have uncertainty in momentum. Momentum is related to speed. So in white dwarfs, if we have a smaller white dwarf, the electrons, the degenerate electrons, will move faster as a result of that confinement. Okay, everybody hear that? That's kind of a big deal. Okay, in fact, I'm hopefully motivating you right now. This, my friend right here, this is Subramanian Chandrasekhar. Everybody say his name. Subramanian Chandrasekhar. And he discovered something really quite beautiful. He found out that the more massive, okay, again, the test is coming. Hopefully pay attention. The more massive a white dwarf is, the smaller it becomes. This is weird, right? This is not the way normal matter works. If you have more atoms, you would expect it to be a larger thing, but that doesn't work with white dwarfs. The force of gravity causes those nuclei to smash together as close as they can be. The larger the mass, the smaller the white dwarf. And so what happens to the speed of the electrons? The smaller the white dwarf, the faster they move. Does anybody know the speed limit for the electrons in our universe? It's the speed of light, right? So this is it. You can't go faster than the speed of light. If you try to make it go faster than the speed of light, guess what? It fails. And that means the white dwarf fails. It cannot exist. Uh-oh. Okay, can we just go with special relativity?
Well,
not general relativity? Is that fair? Go ahead.
It's the speed of light within the medium.
One more time, I can't hear.
The speed of light within the medium.
Oh, yes, absolutely, absolutely, yes.
Just
Okay,
one.
good point. Thank you, that's a very good point, absolutely. The speed of light in the medium, excellent, good job. So that's the deal. So we know that there's a limit to how big a white dwarf can actually be. So if you haven't heard of it before, this is known as the Chandrasekhar limit. So for our sun, which is mainly carbon and oxygen, it turns out it can't be more than 1.4 solar masses. But we don't have to worry about that. We're only going to have about a half a solar mass. So can the sun exist as a white dwarf? You know the answer.
Yes.
Absolutely, no problem. That's less than 1.4. The electron degeneracy pressure can do the job, right? It can hold gravity back, no problem. Okay, so one of the, it's kind of amazing. when you understand how big these are, right? This is our planet, and here's Sirius B, and what do you notice? They're nearly the same size, right? And so when you take a star-sized mass and you shove it down to the size of a planet, what happens to the density? And so those of you who like scientific notation, 10 to the 9th is a typical density for a white dwarf. That's 1 billion kilograms per cubic meter. I forgot to bring my prop. I was supposed to bring some dice. I was supposed to bring some white dwarf material. I was supposed to bring a die. Everybody has a die at home. You roll the dice. So everybody knows how big that is, right? That's a cubic centimeter. 1 cubic centimeter of white dwarf material is 1,000 kilograms. That's as much as a car, right? It's 2,200 pounds. A couple other things, or actually just one other thing, I guess, right? One other thing. The surface temperatures can range, but they're pretty hot, right? They're generally pretty hot. So that's why they're producing the ultraviolet light. So some of you guys are going to keep me on track. I know I'm going a little over our time. Can we go a little bit longer? You guys okay?
Oh yeah.
Okay, here we go. All right, keep going. So one of the things I think is really cool is to know that white dwarfs will cool off eventually, and they're going to be called black dwarfs. So how many black dwarfs have we seen? And the answer, of course, is 0, because there's not enough time. Our universe is only 13.8 billion years old, and it turns out it takes probably close to trillions of years. Okay, so that was one of the estimates I read. So it turns out they just haven't cooled off yet. Another interesting thing, because I know I have some really cool technical people here, in the early days when the white dwarf is very hot, it turns out there's more than one mechanism for losing energy. Some of you might find this cool. It turns out there's a mechanism for losing neutrinos. And even though neutrinos are not heat, by losing those energetic particles, the white dwarf will be cooling off. So there's a more rapid process when the white dwarf first forms. It can cool off by radiating not only heat energy in the form of black body radiation, but also through the neutrino loss. Okay. So now what about if you've got a companion? What does it mean? You've got more fun in life, right? Does anybody agree? With a companion, you've got friends, you've got friends in need. Okay, so if you have a companion, here's an example of a red giant with a companion white dwarf. Then there is a mass transfer process that takes place. Some people call it a symbiotic binder. I kind of like that name, pretty good, right? Symbiotic. They're kind of mutually dependent, although I'm not sure what the red giant gets from this, but anyway, that's the name, I didn't make it. So there's a couple of things that can happen, and one of them, I've been waiting for one to happen for quite a while. Some of you are also in that boat, waiting for a nova to happen. That didn't happen in September like they said it would. And then the other thing that can happen is a type 1a supernova. So if you haven't heard about that, I'm going to tell you about those two things today. So this is the one we were hoping was going to happen this year. It's called T Corona Borealis, TCRB. And actually what's really neat is this is a recurring nova. And so that mechanism is quite beautiful. It turns out that the red giant feeds the white dwarf. And when enough material collects on the surface and the temperature reaches the critical fusion temperature, the hydrogen can begin fusing, and it will last just for a few days probably, but it'll brighten and then it'll fade away over a series of weeks or even months. And this last happened in 1946. And it turns out the estimate for how often it happens is every 80 years. So can you do the math? Okay, so it would have been 2026. It turns out it might be just a little bit under. In fact, sometimes it's 78 years. And so 78 years would put it 2024 this year. Okay, so in fact, there was a high expectation it could have happened this year. Those of you who know how to find Arcturus, you can find Boötes. Next to Boötes is Corona Borealis. And then this is T. It's going to be over here. This is the only, actually I don't see SagA. I thought SagA, maybe they call it Gemma. Okay, anyways, maybe there's a second name. Anyways, that's where we wanted to see it. It didn't happen. What happened? I don't know. I'm not sure what happened. But it looks like this is the data that they were going from. The event in 1946 is actually very early in actually it was 1945, I think, right at the end of 1945, okay. And then there was a little dip that happened just before it. So I can't, my laser's dying. But this little dip that you can see, can you guys see that? You can't see my map. Okay, I'll just point to it. There it is, thank you. Perfect. Oh, look at it. I got my extra laser, thank you. And then you can see the jump in brightness. The brightness is going up as you go up, and you can see it got up to the number 3. If you don't know magnitude scale, 3 is pretty bright. It's not like, so bright that you can't see anything else. It's actually dimmer than the North Star. The North Star is a magnitude 2. But anyways, the prediction for this nova has been that it might brighten to the level of the magnitude 2, which would be equivalent to Polaris, which is kind of neat. But it didn't happen. So we're looking for it to happen in the near future. You'll read about it. I hope you'll take a few minutes to go try to find it if it happens. You might have to get up early in the morning, starting in January. Right now, it's very difficult to see it right after sunset. For a very short while, you can catch it. But I'm hoping that it waits until after it leaves the sun area, and so then we can actually see it. All right, this is the data. Actually, I downloaded this data today. This is amazing. We can download this data. This is from AABSO, and this is the visual data. I don't really see too much of a dip. I read about the dip. I don't really see it in the data. It looks kind of like a regular oscillation, not really something that I would be like, oh, there's the dip. But I just wanted to share. You can download this data. It's pretty amazing. There's links. Do we share our slides? I can share the slides. If you're interested, I'm happy to share all these slides with you. A couple of details which I found really interesting. The red giant has a mass of about just a little more than the mass of our sun, 1.12 solar masses, but the mass of the white dwarf is 1.37. Does anybody remember the Chandrasekhar limit? That was 1.4. Okay, so I'm not going to say that it's going to happen. It's definitely not. But there is a little slight chance that this thing could get up to 1.4. Maybe not this time, but sometime in the human future, right? When we look for the nova, it's not going to be a nova. It's going to be something else, right? So keep that in mind. It's not far from the limit, right? Okay, so the orbital period, it orbits once every 228 days, and the separation distance is pretty small, about a half an astronomical unit, pretty cool. And it's located almost 3,000 light years from Earth. Okay, so as we heard, right, as you're looking 3,000 light years away, we're looking at it as it was 3,000 years ago. Okay, so what if you are really close to that limit? Something interesting happens, right? If you get enough mass added to your white dwarf body so that you're above the Chandrasekhar limit, the electrons would have to move faster than the speed of light. They can't do that. Then the whole thing begins to collapse almost instantaneously. And all of the material, the carbon and oxygen, fuses in a runaway nuclear fusion event. And that's the thing called a type 1a supernova. Okay, so now you know. Type 1a supernova, pretty cool. These are pretty neat. For many, many years, they've been used to measure distances in our universe. We call them a standard candle. And the thinking was, I'm going to go through that if they're 1.4 solar masses and they explode, then we know exactly how much energy was released in the explosion. We can say what their absolute magnitude was and compare that to what we see, and we can get the distance from that. Okay, everybody like that idea? Doesn't it sound great and so good? Okay, but part of my talk was to learn things that I didn't know yet, so I'm about to share them with you. Okay, so here we go. It turns out, yes, you can do that. You can normalize that light curve. Almost any of them can be normalized, and you can use this idea to measure the distance. But recent research has shown something interesting. Some of these type 1a supernovas are not 1.4 solar masses. Okay? Wait a second, right? Something's going on. So anyway, this should have been the right answer, and for many years we used it that way. But we've got some new stuff to talk about. So another mechanism that people had figured out a long time ago is you don't need to do what I told you before. You don't need to have a red giant feeding the white dwarf. You could just have two white dwarfs, right? If the red giant dies, by the way, it's also going to leave behind the white dwarf. And as they orbit each other, they'll create gravitational waves, and they'll gradually come together and eventually merge. And if the two white dwarfs together make a mass more than the Chandrasekhar limit, what's going to happen? A type 1a supernova. But this may not be 1.4 solar masses, right? It's just anything above. So it's not a definite number anymore. So I'm not sure how you feel about that. I was a little disappointed to hear that my great standard candle was not quite so standard anymore. But wait, there's more. Okay, so this is my last thing. Oh, so that was this is actually developed by, this is an AI. This is ChatGPT's picture of the merging white dwarfs. What do you think? Pretty exciting, right? What do you think? And that was free, by the way. You can just do that. Just go, show me a picture of something, and it'll show you a picture. Okay. All right. So, I think I skipped a picture, didn't I? I skipped a picture. I did in the very beginning. Oh well. Okay, but there's another way, and I'm sorry to tell you that there is actually a really exciting new mechanism. 2022 is the first time someone identified this as a mechanism, and it's called a double detonation. Double detonation, you can write that down. But what is this? This takes a white dwarf, which is underneath the Chandrasekhar limit, and it has a red giant, which is actually at a very advanced stage of ejecting its material. It's no longer ejecting hydrogen, it's ejecting helium. And the helium is being collected on the surface of the white dwarf. And it turns out that the detonation of the helium is a much more powerful event. And so one of the ideas is that this ignition of the helium will cause a shock wave around the white dwarf that then generates, this burning generates a shock wave which projects into the center of the white dwarf, which triggers the fusion of the carbon and the oxygen. So the detonation of the helium causes a detonation of the carbon, a double detonation. And this way, a white dwarf can explode even though it's below the 1.4 solar masses of the Chandrasekhar limit. And this may be the answer. It may actually be that this is really what's happening most of the time. So some of the supernova people are saying, we've never seen this before, but now that we have, we're going to start looking for it. This could actually be a more common mechanism for generating the type 1a supernova. Okay, so that's cool. And they do look different. So if you want to go, there's a website at LCO. Everybody know LCO. They're awesome. There was a presentation by a researcher at one of the Astronomy on Taps last year talking about this. But the interesting thing is that, so there's some, let me see if I just read this. So astronomers have had computer models that do these double detonations for decades, but they didn't fit any of the observations of the type 1a supernova. And so they thought that the helium shell had to be thick, right? So you had to have a lot of this helium build up before it would be enough to trigger the shock wave. But it turns out, as much as 15 to 20%. And so, but in recent years, we have found examples that look just like this double detonation. And so this is probably going to be one of the answers coming up. Okay, I think I'm just about done. So thank you very much. I'm going to show you my first picture, so I'm going to go back to my first picture. Sorry about this. Wait 1 second. Right, here we go. This was my first picture. Oh, sorry, I just skipped it. I don't know what happened. I thought it would be funny if, you know, white dwarfs, if you go, Snow White and the White Dwarfs. I said, ChatGPT, would you make me a picture of Snow White and the White Dwarfs with a white dwarf? And they said, no, I can't do that. Would you like to have a picture of a fairy princess with some mythical creatures with her? Sure, why not? So ChatGPT, I want you to pay attention, gave me a picture of a fairy princess. She's really weird looking. And seven special creatures, because everybody count seven, right? That's what ChatGPT told me. But it did make a very nice white dwarf up there in the sky. Isn't that cute? All right, thank you, everybody.
Yeah.
My only question is, without opening up a whole nother speech, is there anything in common between a white dwarf and a neutron star?
Absolutely.
Other than the fact they're about the same size.
There's a lot of similarities. Actually, one of the things that's super cool is the formation of the neutron star in the first place. Is when the core, it's also called a core collapse supernova, type 2 supernova. And so the neutron star forms because the electron degeneracy pressure in the core of the star is not sufficient.
Well, I did that.
Yeah, you did that, right?
Sort of like a
But then the cool part, anybody know what happens next? Is the electrons go inside the nuclei where they're not supposed to be, And the protons become
Neutron.
neutrons. All right.
And our son's gonna become one of these someday.
A white dwarf.
A white dwarf.
Yep. Not a neutron star.
That's an example of what the kids at UCS, or at City College are getting these days in an incredible course. You guys come back, if you want to meet this guy, talk to him, join the club if you have it. For those members, please give your money to Diane and meet him next Friday night out at the Timbers. We're going to pig out all of us. Don't eat all day, get dressed warm. You're going to be there with
I'm
us.
gonna be here. My wife Mary will be with us.
Oh, bless your heart. Well, I got something for the faculty lounge. Okay,
Very good.
priceless cup.
Oh, I love it.
Makes the coffee taste better.
It'll go with my others. I got a little set now.
Hey, you sometimes you're there with your telescope at Saturday night Star Party.
Of course,
That's
it's my
next week.
favorite night.
Okay, are you coming this?
I will.
You're gonna
I'll
be
be
with us
there.
2 nights in a row.
I'll be there.
Okay.
I'm ready to come out. Week from tomorrow night.
Okay, you got it.
Star Party.
And then we'll talk about exoplanets and life on them and all those other things in a month on January 3rd. Thank you, everybody.